guys, welcome back. It's Mrs. Webb here. So today I wanted to chat with you for just a little bit about solubility in solutions. And when we talk solubility specifically, what we're looking at is how much solute we can dissolve into a solution. And generally we're speaking about how much solute at a given temperature, because solubility is very, very temperature dependent. So I'm just going to add a little side note for you here that you may want to add into your notes. So solubility is amount of solute dissolved in solution or dissolved into solution at a given temperature, because it'll change. And you guys intuitively know this, because you know that if you put a couple tablespoons of sugar into a cup of cold tea, a cup of iced tea, you're probably going to end up with a fair amount of solid sugar at the bottom of the cup that won't dissolve into the iced tea solution. Now, if we heat up that tea, you can probably put about the same amount of sugar into the tea, and you'll notice that it completely dissolves into the solution. So it is very temperature dependent. And when we talk about a saturated solution, we can talk about it in terms of percent weight per volume, percent volume per volume, parts per million. But more often than not, we generally speak about it in terms of moles per liter, since that happens to be what we talk about most in chemistry when we talk solutions. So I have an example for you here that says the solubility of sodium sulfate solid in water, and notice that they're telling you the temperature, because like I said, the solubility is going to be very temperature dependent. So they're telling you that this particular solubility is at 0 degrees Celsius, and they're telling us that at 0 degrees Celsius we can dissolve 4.76 grams per 100 grams of water. Generally that's how you'll see it represented. We can dissolve 4.76 grams in 100 grams of water. And what that's telling us is that we can dissolve 4.76 grams in 100 milliliters of water. And I'm going to add a little note for you here. Actually, before I add this note, let me just introduce the term saturated solution for you guys. So what this is telling us here is how much solid we can dissolve into this 100 milliliter solution of water at that temperature. And that amount of solid, that maximum amount of solid that we can dissolve into our solution at this temperature. If we put 4.77 grams, you're going to start seeing some of that solid precipitating out of the solution. So you'll see some solid left at the bottom of your container. And that point is what we call a saturated solution. And saturated solutions, we say, are at a point of dynamic equilibrium. That's what's happening when a solution is saturated, or when you are being told that the maximum amount of solid that we can dissolve into our 100 milliliters of water at this temperature is 4.76 grams. And that dynamic equilibrium, what that means is that there's only so much space between every water molecule, and the solid is going to sit, it's going to dissolve into that open space between the molecules. So there's going to come a point where the space is going to fill up, and the water molecules, there's just not enough space between those water molecules to fit any more solid. And that's the point at which the solid starts to precipitate back out of the solution. And the point of dynamic equilibrium, what we say is happening is that we have, let me just grab a thicker marker here so I can show you. We have essentially something like this happening. Just move this up a little bit. And then let's grab a different color. we have essentially something like this taking place. So in this purple arrow, we have solute dissolving into solution. Okay, and in this light blue arrow, we have solute crystallizing out of solution. So it's kind of a funny concept to think about, but when you're at that saturated point where the space between the molecules is completely taken up by solute, so the space between the water molecules is completely packed with solute. What's going to happen is that the solute is going to start to recrystallize, and it's going to start to dissolve out of the solution. But in that instant that it starts to dissolve out of the solution is going to dissolve it right back in. And then solute will start to dissolve out of the solution. It'll recrystallize. And as soon as it recrystallizes, the water dissolves it right back in. And so it's this ongoing cycle of being dissolved, crystallizing out, being dissolved, crystallizing out. And the thing is that when we're observing this saturated solution, we won't actually see the crystallizing out. We won't see that crystallizing form, because as soon as it forms, it dissolves right back in. And that's the point that we call dynamic equilibrium. And this is in a saturated solution. And I'm going to move this up so that you can see this. It's probably too low. So that is a very, very, very important concept for you to understand, is that at a dynamic equilibrium is the point at which the water is holding. It's holding the maximum amount of solute between the water molecules that it can potentially hold at that temperature, because you know that the space between the molecules is very temperature dependent. The colder it is, the smaller the space. The hotter it is, the larger the space between the molecules. And so if the solution is saturated, then the solute is going to dissolve in and recrystallize out, dissolve in and recrystallize out, dissolve in and recrystallize out. Okay, so that's kind of the first little bit of solubility. Now, I just want to check down here before we continue. The other thing I want to tell you about, and I'm just going to keep sliding this on over here. I'm going to make this slightly smaller so that you can see it all at once. Now, the other situation that we can have is we can have a, I'm going to put this in red ink. We can have an unsaturated solution. Okay. And if it's unsaturated, much like the name implies, we can still dissolve more solid into it. So at this point, yes, the space between the molecules is being occupied by some solute, but there's still space left over and we can put more solute in. And so when this happens, if we go back to our colors here, okay, remember that this purple arrow means the solute is dissolving, and this blue arrow means that the solute is crystallizing. So when we've got an unsaturated solution, what happens is that the rate of dissolving is much larger than the rate of crystallization. So dissolving is greater than crystallization. Whereas at dynamic equilibrium, dissolving is equal to crystallization. So I'll add that there for you too. Now, the other type of solution we can have, so let's just highlight these types of solutions. Got unsaturated, we've got dynamic equilibrium or saturated, and I just gave you the third type, supersaturated. And in a supersaturated solution, the rate of crystallization is less than, the rate of crystallization is larger than the rate of dissolving. So the water can't keep up in this scenario, and we start getting precipitate falling out of solution. So dissolving here is less than crystallization. And that's what happens when you have a supersaturated solution and you end up with solid at the bottom of your beaker. So those are the three scenarios. You can have a saturated solution where the rate of dissolving is equal to the rate of crystallization. And at that point, all of the space between the water molecules has been filled with solute. You can have unsaturated, where the rate of dissolving is much larger than the rate of crystallization. And at that point, you have some solute between the water molecule spaces, but you have lots of empty space still. And then you can have a supersaturated solution where the rate of dissolving is much less than the rate of crystallization. And so the solution can't keep up with the amount of crystallization that's occurring, and the solid ends up precipitating out of the solution. And those are very, very, very important. For you guys to know and understand. So do spend some time thinking about that. These are really good kind of theoretical questions. Can you explain what's happening, right? In terms of, temperature, spaces between water molecules, dissolving and crystallization, etc. Okay. Now, types of questions you might see, we're going to get to. The other thing I wanted to talk to you about is this, because we've been talking about crystallization and all of that. We've talked a little bit about how if we increase temperature for tea, we can dissolve more sugar into it. The thing with the solubility rules, which you do need to memorize, is that solubility rules are different depending on what the solute is going to be. So if you have a solid solute like sugar, solubility rules for solids tell us that the hotter the solution gets, the more solute will be able to dissolve. It's a linear relationship. Okay. With gases are different, because remember that when gases get excited, gases increase in volume and they rise, right? And so gases, when they get hot, will tend to actually escape from a solution. And so gases will become less soluble as the temperature rises. So they have an inverse relationship with temperature. Liquids we won't talk about, but generally liquids tend to follow the same rules as solids. And liquids will generally increase solubility as you increase the temperature as well. So solids and liquids have a linear relationship with temperature. Gases have an inverse relationship. And these are two important kind of scientific words that you should keep in mind when we talk about immiscible. And it doesn't have to be immiscible liquids, it could be just immiscible. Immiscible means that whatever solute you're trying to mix into your solvent, that particular solute will not mix. It's immiscible. It's kind of like, I always use the example of courtroom dramas when things are getting really heated in the courtroom and somebody brings in brand new evidence and the other lawyer says, that's immiscible evidence, right? That means that you can't bring that evidence into the trial. So immiscible means these liquids will not mix, just like oil and water, for example, right? So one will be non-polar, the other one will be polar, which means it'll be immiscible. If both solute and solvent are polar, they will be miscible. That means that they will readily dissolve into the water or into whatever your solvent will be. Okay, so those are important terms for you to memorize. Now, the other thing you need to see, which is kind of a little unnerving at first glance, is this particular graph. I'm going to make it small because I have a feeling you guys won't be able to see it on the screen if I keep it large. This graph is a solubility graph. And you'll notice that it has a bunch of different lines on here. We will give you this graph in a question. You do not have to memorize it or anything like that. We have temperature being manipulated here on the x-axis, and temperatures in degrees Celsius. And then we have grams of solute per 100 grams of water. So we start with 0 grams of solute here at the bottom, and then this is what's responding to the temperature increase. Now, if you notice, we've got a bunch of positively sloping lines. Remember that solids and liquids tend to be directly linked to temperature. They have a direct relationship. So if the temperature goes up, the solubility goes up, which means that all of these positively sloping lines are going to be solids or liquids. The negatively sloping lines, those are your gases because they have an inverse relationship with temperature, right? So a typical question that you'll see, and that we'll get to practice in class, is something like this. A saturated solution of KNO3 is prepared at 10 degrees Celsius. How much KNO3 is needed to prepare a 5-liter solution? So I know that this particular graph tells me grams of solute per 100 grams of water. So I'm just going to come over here to my 10 degrees Celsius line, and I'm going to follow this line. I'm going to extrapolate up to my line until I get to my KNO3 line. And so right here is the KNO3 line. And now I'm going to follow this across to read what is my maximum amount of solute that I can dissolve into my KNO3, or into my solution at 10 degrees Celsius. And if you look here, I can dissolve about 21 grams. I wrote 21 before. I would actually say maybe 22, right? You need to be very careful with how you're reading your graph. But we'll say about 21 grams of KNO3 and 100 grams of water. That means 20 grams of KNO3 and 100 milliliters. And so in this case, it's like we were doing percent concentrations. Here. We're going to set up a proportionality statement. We've got 21 grams of KNO3 per 100 milliliters of water. I want to know in 5 liters, or in 5,000 milliliters, how many grams of KNO3 do I have? So I'll cross multiply, and I find that I've got 1.1 kilograms of solute of KNO3 in 5 liters of water. Okay, so they're generally proportionality style questions. The other thing I want to tell you guys here is that all of these lines, this line, this line, anything that's on the line, this line, these indicate saturated solutions. Okay, so if your point falls on the line, that represents that your solution is saturated. Okay, so the example here with the 10 grams, we followed this up till we met the KNO3 line. That means that we are at saturation here. We've reached the point of dynamic equilibrium. Anything that's located above these lines, that would be a supersaturated solution. And anything that is below the line is unsaturated. Okay. So whenever, if I was to tell you we dissolve, let's say 60 grams of ammonium chloride at 50 degrees Celsius, am I supersaturated, unsaturated, or saturated? So 60 grams at 50 degrees Celsius, I believe I said. So I'm going to follow my 50 degrees Celsius line up. Let's actually draw that in. Until I meet my 60 grams. This is the point where that intersects. Ammonium chloride is right here. So this line is my saturation line for ammonium chloride. And you'll notice that the point is above that green line, which means that I am super saturated at that point. If I ask you, we dissolve 80 grams of sodium nitrate at 30 degrees Celsius. So let's follow our 30 degrees Celsius line up until we reach 80 grams. Right there. And I'll get another color here to highlight with. Here's my sodium nitrate line of saturation. So you'll notice that, let's go with a thinner pen here. You'll notice that I have that much space until I reach my saturation line. So I've dissolved 80 grams. I still have about another 15 grams worth of solute that I can dissolve into this sodium nitrate. Okay. So important things to note about this graph, you need to be able to read it and understand what it's telling you, right? So we need to be able to understand that the lines are lines of saturation. Points above the line mean supersaturation. Points under the line mean unsaturated. You need to be able to do these proportionality questions as well in terms of grams. So this will be something that we'll get a chance to practice together. But if you do have questions, please let me know. And as always, I hope you guys are doing well, and we will chat very soon.